So we have these two important trig limit theorems that limit as x goes to 0 sine x over x, or its flip, is equal to 1. And the limit as x goes to 0 of 1 minus cos x over x, or cos x minus 1 over x is equal to 0. And we have to be a little bit creative, because in order to use those, okay, we need to make sure that it is the limit as something goes to 0. And we talked about this on Friday with the green boxes here. With sine, you can have anything in those green boxes, all three of those sort of match up. So sometimes we do some rearranging, sometimes we just do some general thinking, but now we're going to have to be creative because I have the sine at 7x on the top, but you notice that I don't have a 7x on the bottom. And I have a sine 3x on the bottom, but I don't have a 3x on the top. So this would be actually much nicer, right? If you had this, we need to then get this to have a 7x on the bottom instead of an x, and this to have a 3x on the bottom instead of an x. So we have to be a little bit thoughtful and a little bit thinking. So I'm going to, you see that by adding an x here on the bottom, technically, I've got creative, I multiplied that by 1 over x and this by 1 over x. I multiplied by 1. And so we get creative in how we rearrange things so that it matches up with our formulas. And if it matches up with our formulas, then we can apply it. So let's start with the numerator. If I had this, the limit of 7 sine 7x over 7x, so I wanted that to have a 7, so I added a 7 on the bottom, which would mean I would have to add a 7 on the top. So we can do a substitution here, or I am okay with you also saying, well, if I know that x goes to 0, then 7x would also go to 0. So this limit here, do the substitution if you'd like, but this limit's going to equal 7. Let's look at the same thing with our denominator. I can add a 3 on the bottom, which would mean I would need a 3 on the top. If I do that limit, and again, as x goes to 0, 3x would go to 0. So technically, this is going to be 1. You put the 3 out in front. We can do the substitutions as well. And the denominator is going to go towards 3. Which means this entire thing is going to approach 7/3. If the numerator approaches 7, the denominator approaches 3. Well, we had to be creative in order to make things match up. Again, by the time you get to your AP exam, we're going to figure out a way to do this that's even easier. But historically, sometimes, and depending on who you might get as your professor in university, some are really particular. We can't do the later on stuff without first knowing the squeeze theorem. So historically, this is important for us to figure out as we go along, even though later on, we're going to figure out stuff with derivatives to make this even easier.
Are you muted by any chance?
No.
The smartboard doesn't seem to be picking up.
I think we're good. Did I start my video?
I don't think
think he did.
No, I'm going. Yeah, because if I click on this, it's got a little red dot meaning recording. We're good. Thank you for checking though. Because there were some glitches last week. Some of the videos have no sound. But this one, I think, should have sound. Okay. Next one, be creative. Ooh. We've got a cubed here. Okay? And also, we've got an x there and a 2x down below. So I'm going to get creative. I'm going to cube the bottom out. I'll go blue. Right? Limit as x goes to 0, sine cubed x. If I cube this, I would have 8x cubed. And I can break that up to the 1 over 8 out in front, then 1 sine x over x, another sine x over x, another sine x over x. And our properties of limits say I can bring the 1/8 out in front and then do each of these limits separately, which they're all equal to 1. And I get 1/8 in the end. These feel almost a little bit like identities. You kind of have to manipulate the algebra that you have until it matches up with something that you can do the limit of. So if we can get the limit as something goes to 0 of sine of something over that same something, it's always going to be 1. And then just seeing what we have with things that are left. In this question, we're going to use the strategy of unadding fractions. You know how to add fractions, right? What do you need? You need a common denominator, and then you add your numerators together. Unadding fractions is like, I'm glad I added those fractions together, but it would actually be more helpful if they weren't added together. Right? Could I make both of these over x and unadd them? Because it would be 3x over x plus sine x over x if they were unadded. And maybe things simplify nicely when we do this. And in this case, they simplify really nicely. Do you see that your x's would go away here? And then you just get 3. That limit's going to be 3. And this one matches up perfectly with our formula. So we just get 3 plus 1, and we get a limit of 4. Does this match up perfectly with the formula? Not quite. We have a 3x in there, right? So if we wanted it to match up nicely, what would we need here? We would need a 3x there. How do I put a 3 in there? Well, if I put a 3 in there, I would have to multiply the top by 3 as well. And then the fact that x goes to 0, do you see that 3x would also go to 0? So we can do an application in that situation. We can do the substitution there. I've added my 3's. Right? I am okay if you want to do this. okay with that. Can you see that the 3 would come out in front? And then the limit of 1 minus cos 3x over 3x is going to be 0. I'm okay if you don't do the t substitution. The t substitution is nice because it really matches up, but what I'm really doing here is I'm saying as x goes to 0, it's pretty obvious that 3x goes to 0 as well. Let's really get identity-like. Whew. So we've got x plus sine x over 10x. The only tools that we have that are helpful with limits with sine and cos, first of all, try plugging things in, because if things plug in, we might be doing way too much work when we don't need to. But unfortunately for this one, tan of 0 is 0. So you're dividing by 0, so we still have a problem at this point. But these are the only two limit theorems we have that we can work with. And so now we have to be creative in this question to see what we can do. So just like identities, you usually start questions like this by having the I don't know how to do this at all idea. I better try something. That is your strategy in identities. I better try something. So what might I want to try? Maybe I change tan. Here, I'll do an extra step here. Do you see that tan is, maybe I have the extra steps over here. Tan is sine over cos, right? And if I unadd fractions, and I do the x over sine over cos, and the sine x over sine over cos, or if I think about what do you do when you divide fraction, the top would be over 1, multiply by the reciprocal, because you're dividing fractions. And if I distribute, I would get the x times cos x over sine x plus, and here my sine x's would cancel out. Because I've taken this part here and I distribute it to both of them. What is nice about this? Well, do you see that here you have your sine x over x or x over sine x part? That's our one limit theorem. So now can we break things up? I can break this up to the limit as x goes to 0 of the x over sine x times by the limit as x goes to 0 of the cos x plus the limit as x goes to 0 of the cos x. So now I'm going to do each of these separately. Now the limit as x goes to 0 of cos x is something we can plug in, right? What is cos of 0? 1. So this will be 1. This will be 1. And that will be 1. And 1 times 1 plus 1 is 2. If this was a longer, this is crazy, okay? Again, I won't let you do this on labs, and I expect you to simplify things on all of your take-home quizzes. But technically on the AP exam, you could put a box around this and you would get full marks. They'd be like, that's okay that you decided not to do 1 times 1 plus 1 in your head. You would still get full marks for leaving like that. Even though it seems kind of like, I actually find it's really difficult as a math student to stop, right? If you had 1 times 1 plus 1, I think it'd be very hard for you not to write 2 and stop there. But you technically would be fine to leave it like that on a long answer on the AP exam. Any arithmetic does not need to be done. All right, our last one, as x goes to 0, cotangent 2x over cotangent 5x. Cotangent is cos over sine. So you could change those with identities. And then multiplying by the reciprocal gives you cos 2x sine 5x, sine 2x cos 5x. Based on what we did in the top left of this page, where we got that answer to be 7/3, do we have any guesses what you think this one should equal? 5/2? Okay, we'll find out. So we have this, which we could break up by multiplying everything over x. So if I take this and I multiply it by 1 over x, and I take this and multiply it by 1 over x, because I'm wanting to get things like this, right? So again, we can split things up and look at our numerators first. We've got sine 5x over x in our numerator, and we can multiply that by limit as x goes to 0 of cos 2x. What do I want with that sine 5x? Technically, I want a 5 here, right? So that it for sure matches up with the 5x and the 5x, which means I would need a 5 up there. This limit is going to equal 1, because as x goes to 0, cos of 0 is 1. And you just get the top part to be 5. Next, our denominator. Same thing. I want a 2 here, so I put a 2 there. And that 2 on the top I could bring out in front. Could do the substitution if I wanted to. But I'm okay if you just make that 2 at this point. And it is 5 over 2.